Hello, I'm Bonnie,
And I'm Tyler.
and this is a novel addition to sentence completion models.
So the task for our project is the sentence completion task. For this, you can think of SAT-style fill-in-the-blank questions that require essentially like domain knowledge of the connotations of words, as well as the ability to parse grammatical structure in order to determine which word fits best in the sentence.
Some existing approaches we found from a literature review included n-grams and skip-grams, so words close to the candidate word, latent semantic analysis, recurrent neural networks, and positive pointwise mutual information. And that one in particular did the best.
However, a lot of these models encountered the same problem, which is that the answer choices for SAT-style questions tend to be obscure vocabulary words, which may not exist in the model vocabulary. And if they do exist, since they're uncommon, their associated values, like word vectors or PPMI values, might be noisy.
So just to illustrate this a bit farther, here's some sample questions.
If you take a look at the question on the right, you'll notice that in fact the answer choices for this question are especially obscure, to the point where they're not even represented in the training corpus for one of our data sets. So in this case, using synonyms or hypernyms would be necessary.
Currently, we have two data sets that we're working with. The first is the Microsoft Research Sentence Completion Questions, which come with about 1,000 sentence completion questions, along with its own training corpus, which is drawn from Project Gutenberg. We've also compiled a data set of SAT questions, about 300 of them, and for this data set, we are going to use a corpus from the New York Times, which comes from the GigaWord corpus.
So the model we've chosen to use is made up of several different components that are drawn from various previous publications. And in addition, we've added our own synonym and hypernym substitution method. First, we're using discounted positive pointwise mutual information, which by discounted we mean we give less weight to infrequent words. And this is because less frequent words tend to have a greater amount of noise. In addition, we filter stop words based on part of speech. For example, filtering out determinants and pronouns. We use normalized versions of non-stop words in order to deal with strange grammar or like abbreviations that might have been encountered. We give extra weight to the direct ancestors of the answer choice based on a dependency parse of the question. Finally, for our synonym substitution mechanism, we use WordNet to look up synonyms and hypernyms of any word that's not in our vocabulary. We then filter by relevant part of speech, so the part of speech we expect this word to have. And then we order the synonyms and hypernyms by the word count of those synonyms and hypernyms, therefore getting the most common version of the synonym. And then whatever word comes up with the highest score in terms of those features we use in our model.
As for evaluation metrics, this is the rare NLU application where accuracy is actually a faithful measure. So the number of test questions we get right is actually a good measure of how well our system is performing. Also, since we're using standardized test questions, we're going to calculate a placement percentile for our system so that we can compare our system to human performance as well.
Now we present our results. As you'll notice by looking at the table on the left, adding synonym and hypernym matching improves our accuracy above the baseline on both the MSR and SAT datasets. In addition, adding stop word removal and using discounted PPMI further improves our accuracy.
Before our final deadline next week, we hope to train using larger vocabulary sizes because while our intermediate results might not show it so far, our error analysis does show that still our main errors are due to the fact that some words just don't appear in our vocabularies. We also want to try using sentence-based contexts instead of window-based contexts for the PPMI parts of the model. Finally, we've done a lot of work so far refining our model for the Microsoft Research dataset, and we want to do the same amount of work for the SAT dataset. That concludes our progress on this project so far, and thank you for listening.